Hi, good evening everyone. Hope you all are doing fine. Today we are going to discuss the waveform synthesis of transient analysis. Before that, we will be taking the how to find the Laplace transform of differentiations or what are the properties involved. Again, same for the Laplace transform of integration of the signal, and we'll also discuss the that is your initial value theorems and final value theorem, because these two theorems are specially applied for the causal system or causal signal, that is we are inherently discussing in the network theory analysis. Okay, so let's start. Hopefully everybody can hear me. So a little bit about the your continuous signal and discontinuous signals. We know that u of t is equal to 1 for t greater than 0 and 0 for t less than 0. What is the value of t equal to 0? That is because it is a discontinuous. That means the signal looks like this, 0 and this is t. So here let's say this is your x of t. X of t minus or t equal to 0 minus, right, equal to 0. What x of t equal to 0 first is your 1. Okay, but what about one second, yeah, what about the signal? Let's say x of t is equal to sin t ut, and another signal is x2t, which is equal to e to the power minus 5t ut. Whether these two signals are continuous or discontinuous, it is they are continuous signal. Okay, there is no discontinuity, no discontinuity at t equal to 0. The mere multiplication of ut does not make the signal discontinuous. It is a indication that the signal sin of t starts from t equal to 0. Same way for e raised to the power minus 5t ut. For example, if you draw the sin t, it looks like this, and here t equal to 0. My drawing will be there. But when you do the sin t ut, that means we reject the signal below t equal to 0. We reject the signal below t equal to 0. But a mere multiplication of ut does not make x1 discontinuous. So I can write x1 t equal to 0 minus is same as the x1 t equal to 0 plus, which is 0. And same way you can also say that x of 2 t equal to 0 minus is equal to x2 t equal to 0 plus, which is 1. It makes significant, okay, when you finding the initial and final value, initial and final value of the signal. So for these continuous type of signal, you can very well represent x of t equal to 0 minus, which is equal to x of 2 equal to 0 plus, which is we can write x up to t equal to 0. So that does not makes any difference. But when you take a discontinuous signal, that will make sense. So you will have two form of initial and final value. That means initial and initial value theorem. I mean to say initial value theorem, it does not takes the accounts of t0 minus, only t0 plus. I mean to say when you are calculating the differentiation and integration of the signal, whenever you have a discontinuous signal for differentiating, you have two sets of value, one for the t equal to 0 minus and one equal to t equal to 0 plus. But for your comfort, I can say it is easy that most of the signals you will encounter in the network theory are the continuous in nature. Okay, let us discuss the Laplace transform of differentiation. Okay, we have a signal x of t. Okay, we want to you know the signal x of t has the Laplace transform of capital X of s. We need to find Laplace transform of, what is the Laplace transform of dx of t upon dt. This is very useful when solving the differential equations. By definition, I can write 0 minus to infinity dx of t upon dt, okay, e raised to the power minus ast t. Okay, so use the by parts rule. That is, this is one function, this is another functions, right? Take integration of this function, take the differentiation of these functions. Okay, okay, multiplication. First function, let's say this is your x1 and this is your x2. So first functions and integration of I am assuming this is x1 and this is x2. This is a simple by parts rule. That is, it first function it st and the integration of the second function. When you take the integration of the second function, it will be simply x of t, and limit is 0 minus to infinity minus integration 0 minus to infinity, integration of second function, differentiation of the first functions, that is minus a s e to the power minus st that dt, this one, right? You can easily say that when this s when t tends to infinity, e to the power minus infinity 0, okay, 0 and 0 minus x of 0 minus, when it is 0, when you put the put the limit 0, this becomes 1. For these terms we got this. Now come to the next term. So minus of minus, that is your plus, and we come out with the s. Okay, we come out with the s, and remain, what remains, that is 0 minus to infinity x of t e raised to the power minus s dt. If you identify this becomes x of s by definitions minus x of 0 minus. Clear? So this is the differentiation. That means s multiplied by the Laplace transform of xs minus initial value before the switching happens. Initial value before the switching happens. Similar way, you can extend, if you know this, you can extend it to the, for example, t square x of t to t square, Laplace transform of. So I can write, first of all I write d of dt of d of dt xt. But we know that this is the s Laplace transform of this, that is L of dxt upon dt, right, minus finding the initial value at 0 minus for these functions, that is d of dt x of 0 minus. And you know that Laplace transform of this, because we have already calculated here, that is x of s minus x of 0 minus dx upon dt 0 minus, that is s square x of s minus x of 0 minus s into x of 0 minus dx upon dt 0 minus. Very simple. If you know only the Laplace transform first differentiation, then you can easily find the any differentiations, that is the Laplace transform of any higher order differentiation. For example, you can easily write in this sequence, that is Laplace transform of dq of xt, the third derivative xq x of s minus s square x of 0 minus s dx upon dt 0 minus d square x upon dt square 0 minus. What do you see here? Okay, what you see here, to find the Laplace transform of first derivative, you need one initial value, right? Similarly, to find the Laplace transform of second derivative, you require two initial value. Similarly, for third derivative, you require three initial values. So, number of derivative and number of initial value requirement are same. Okay. So, let us move to the another thing I want to say here. If the signal x of t is continuous, okay, if signal x of t is continuous, so so we don't need to designate like 0 minus 0 plus. Instead, we can simply write, for example, Laplace transform of dx of t dt is equal to s x of s minus x of 0 if x of t is continuous. If it is if you want to find the Laplace transform of differentiation after switching, and provided you have two different values before switching and after switching, so you can write let for t equal to 0 plus. So you can simply write Laplace transform of dx of t upon dt, which is equal to x of s minus x of 0 plus. Similarly, you can extend. So this differentiation does not make sense. For example, for t0 plus t0 minus, if x of t is continuous, so both can be replaced with this one equations. Try to understand what I say. Many people are not clear why when we take 0 plus, when we take 0 minus. Okay, right? 0 minus when you take when the initial values are there, right? And you want to convert the differential equations into a algebraic equation by taking the Laplace transform. Okay, clear? If the signal the x of t is continuous, then no issue whether 0 plus 0 minus does not make any sense. If it is discontinuous, you have to make this one for 0 plus, you have to use this equation, this relations, and for 0 minus as I have already told, this one. Okay. Similarly, Laplace transform of integrations. Okay. A Laplace transform of integrations. So I will directly write 0 minus to t x of t dt as the Laplace transform of x of s upon s. It is starting from the 0 minus. Okay. And here is the preconditions. What is the preconditions for that? Precondition for the integral is the precondition for the integral is the if I write the x of t must be exponential order. That means, okay, how the exponential function looks. Okay, like ut, how it looks, decaying exponential order. So this is decaying, and for t equal to 0 means from here onward we neglect this, and we have the integration minus infinity to t x of t dt. Then this will be there, then additional term will be there, x of minus 1 0 minus 2s. What is this x of minus 1 0 minus? This is very important relations. Minus 1 0 minus x of minus 1, this is the minus infinity to t x of t dt evaluated at this integral, evaluated at t equal to 0 minus. What is that example? Okay, what is the practical significance? I will be explaining. Okay, the practical significance I will be explaining. See here, we know that suppose x of t is equal to it, current, right? X of t equal to it, then integration of x of t dt is equal to integration of it dt, which is equal to total charge. That means suppose current is going, so you are minus into this up to this charge, total area is the total charge. So you can relate now. What is this then? X of minus t 0 minus, which is same as the integration of it dt evaluated at t equal to 0 minus. What does it say? Can anyone say? This is the initial charge. Initial charge. Understood? This is your initial charge. Like we say, na, capacitors have some initial charge. Okay. What can be other x of t in with respect to the network theory? X of t can be Vt, voltage, right? If x of t is voltage, so integration of Vt and dt, what is that? Integration of Vt dt, if you know the Lenz's law, Faraday's law of electromagnetic induction, that is the psi. psi, that is the Fox linkage. Fox linkage. Then x of minus, that is the integration of vt dt evaluated at t equal to 0 minus is the initial Fox linkage. Initial flux linkage. And same way you can also calculate for the t0 plus. If it is a continuous, t0 plus x of 0, t0 plus and t0 minus same, right? And if it is has a discontinuous, like some involvement of impulse or step functions, then you have a two different values, or you can say the x integration of x of t evaluated at 0 plus is not same as the integration of xt at evaluated at 0 minus. So just you need to remember these important formulas, relations, and up to some extent I have explained the physical significance. Let's move to the initial value theorem, that will be covered also in the signal and system. The preconditions are x of t must be causal, that is it should not exist for t less than 0. Xl and xt and its derivative must be Laplace transformable. X of t must be causal and x of t and its derivative x of t d of x of t dt must be Laplace transformable. Must have, we can say the must have Laplace transform, right? And x of t do not contain any higher order singularities like del t, del square, the differentiation of the del t upon del t, they are called the higher order singularities. Okay, del t singularities and higher order singularity is the differentiation of impulse functions. They should not contain the conditions, and xt must not have higher order singularities, must not have del t and other higher order singularities. Then you can say x of 0 plus, that is the initial value from the Laplace transform, limit s tends to infinity x x. Suppose you want to find the initial value, okay, that is particularly x of 0 plus, then you can from Laplace transform itself you can find out, that is limit x tends to infinity s x. Okay, final value theorem. This is called the steady state value also. Steady state value, right? So steady state value means as t tends to infinity, as t tends to infinity, what is the value of x of t? We simply limit s tends to 0 as xs. What is the preconditions? Same conditions as above. In addition, s xs, or you can say s xs have all roots in left half of S plane. That means when you have a S plane, the roots of this must be this side, left, not even j omega axis, okay, only on the left hand side of S plane, then you can apply. So let us apply some initial and final value theorem. Let's x of s has been given like this. Or you can say s plus 2 into s plus 3. What is the initial value? What is the x of t at t equal to 0 plus? You can easily see that numerator and denominator have the same order. So it has a the xt has a del t term, okay, xt has a del t term, so it does not have initial value. So x of t does not have an initial value. Another example, x of s is equal to t upon s plus 1 into s plus 2. Of course, one s is, so it doesn't have any singularities, so you can easily found x of t equal to 0 plus as the limit s tends to infinity s into xs, so 3s x square upon s plus 1 into s plus 2. So by using the infinity series limit, so you can write 3s square upon s square plus 3s plus 2 limit s tends to infinity, and limit s tends to infinity equal to 3, divide all the terms by s square plus 1 3 upon s plus 2 upon s square. When limit s tends to infinity, this 0, this 0, so ultimately answer is 3, right? Final value, x of s is equal to 3 s plus 2 into 4 s into s minus 3. What is the final value? So x of t tends to, or t equal to infinity, is the limit s tends to 0 s xs, so 3s into s plus 2 upon 4s into s minus 3. You may forgetting that you calculate and you will find that 3 by 4 and into 2 upon minus 3. This is wrong. This cannot be, because here you see that one pole at the, or one root of the characteristic equations has the one root in the right half of S plane. So you can say that it is increasing. So you have a final value of minus infinity. Okay, so final value will be keep on rising without any limit. If you have x of s like 2 into s plus 1 upon s into s plus 2, then what is the limit final value? Limit t tends to infinity, x of t is equal to limit s tends to 0 s xs, that is limit s tends to 0 2 into s plus 1 upon s plus 2. So it is, when I put the s equal to 0, 2 by 2 which is 1, right. Let us move to the next topic, waveform synthesis. How to write whenever you have a waveform, how to write it mathematically, and how to find the Laplace transform. Suppose I given you x of t, write it mathematically. So what we will do here, you can easily see that is a rectangular pose. So you can launch a ut. You can launch a ut at t equal to 0, and somehow you want to cut it from here. How? How? Then if I launch another ut at t equal to 0, t equal to 2 but negative, then this positive and this negative cancel out, so become 0, and you have remain this. So how to write that? Then x of t is equal to 1 is here, so u of t. Then where we want to launch a negative, that is minus u of t minus 2. This is your u of t minus 2, but it is negative, so we have put a negative sign. Clear? Yeah, no issue, but just I stopped it. Okay, so let us start. Okay, then how will write this one? Okay, how to write this? Let's say x1 t. This is a straight line up to here, so I will launch a straight at t equal to 0. What is the slope here? 1 by 1, that is slope is here 1 by 1. I launch, this is 1 and this is. But when I launch a slope here, but here the slope is in the reverse directions, but before making a reverse directions, when I launch the another signal here of same slope but in opposite directions, what happens? Same slope, like this is 1 by 1 and this is also 1 by 1, but negative slope. So what will happen here? The signal at this point will be this slope and this slope cancelled, and signal will remain like this, right? What I need to do to make a turn here, I need to do launch another signal of same slope. That means I have to make another ramp at t equal to 1 of this slope. That means again I am showing in the different color. So there are two ramp launched in the negative slope at 1, so that this can be bent. Understand? When I launch 1, it becomes straight. Then I need the signal should go down. That means I'll launch another one here. Then, but here it is terminated at this point. That means I will launch here. What is the slope here in the positive direction, so that this and this get cancelled. Okay, so I will write it x of t is equal to, first is the slope, that is, and I am launching at t equal to 0. So RT, you know RT? RT is the TUT. Okay, slope is here 1 and here negative slope of twice, that is minus 2. Where you are launching? T minus 1, right? Then here a positive slope plus R of t minus 2. This is the RT, this is the minus 2 or t minus 1 because launched at t minus 1, and then here we launch positive direction to cancel the negative slope, that is RT minus 2, or you can write like this, t u of t minus t minus 2 t minus 1 u t minus 1 plus t minus 2 and u t minus. Clear? Okay, the same way you can find the Laplace transform. What is the first function? Laplace transform of first function. First function was x of t equal to ut minus u t minus 2. So x of s will be the, what is the Laplace transform of ut? 1 upon s minus, it is also 1 upon s but shifting property, minus 2s, that is 1 upon s 1 minus e to the power minus 2s. Simple. Then second one was the x of t is equal to r of t minus 2 r of t minus 1 plus r of t minus 2, and you know the Laplace transform of this. What is the Laplace transform of x of r of t? That is 1 upon x square minus 2 upon x square e to the power minus s plus 1 upon x square e to the power minus 2s. Simple. Is it clear? Now find the periodic trains of poles and the Laplace transform of periodic trains of poles starting from t equal to 0. This is a 2a, 2a, then 3a, then 4a, 5a, and goes on. This is your x of t. It's a periodic. Either you use the relation in the last class we have studied, Laplace transform periodic signal, or you can first write the x of t in the using the waveform synthesis. X of t equal to, for this you can write, earlier we have written u of t minus u of t minus a, for this plus 2 u of t minus 2a minus 2 is a 1 na? Okay, 1 na, so no 2, so u of t minus 2a minus u of t minus 3a. This goes on like this, yes or no? So x of s will be the, all are s, so 1 minus e to the power minus as plus e to the power minus 2as minus e to the power minus 3as, then plus goes on up to infinity. If you are assuming that e to the power minus as magnitude is less than 1, okay, then you can write with the infinity series 1 upon 1 minus r, that is r is the, r means common ratio, that is e power minus as, that is 1 upon s into 1 upon 1 plus e to the power minus as. How to write the Laplace first you write how to write the x of t of a full wave rectified wave. Suppose you have been given full wave rectified signal. That is from t equal to 0, so pi, 2 pi, 3 pi, and goes on, right? So then what is the this is your 1 na? No, 1. So how to write the equation of this? If the half of the time period is pi, so this is the sin t, because sin t is 0, sin pi 0, and sin pi by 2 will be here, that is half, sorry, sin pi by 2 1. So first wave is your like this, but I need, here is a positive, second pulse is positive, but here is a negative. What will do? I will launch a sign here again, I will launch a sign here again, so this cancel, we have only one pulse, yes or no? We have only one pulse. First sin t, then launch a sign here at pi, so start writing x of t is the first one is the sine t. Then launch a sine function at t equal to pi. So that means delayed by the pi, that is plus sine t minus pi. That means for this I got this pulse. Okay, whenever writing this, when you are writing this, you also write u of t minus pi. Otherwise, it will be wrong. Okay, u of t minus pi, because sine t minus pi is different from the sine t minus pi u of t minus pi. Do you agree or not? Sine t minus pi, only sine t minus pi, and your sine t minus pi u of t minus pi. Sine pi, this is a sine t, and sine t minus pi is the delaying by pi. That means it will goes to here. The signal will be look like this. When you delay by pi, signal will be look like this. Okay, but sine t minus pi u t minus pi means signal will, this portion will be not there, and you will have only this portion. Okay, now come to the second pulse. Second pulse will be the, this is the pulse 1. Pulse 2 will be the, this one will be the N1 sine of, again you launch here, sine of t minus pi into u of t minus pi. When you launch here, then you will again launch another pulse here, so that you have cancel this. The second pulse will be having, you will having the second pulse, that is sine of t minus 2 pi u of t minus 2 pi, and goes on like this. When you add all these things, you will have sine of t plus 2 sine of t minus pi u t minus pi, plus again you will another pulse, so all the terms will be again 2 multiplied by 2 pi and u of t minus 2 pi, and goes on. And find the Laplace transform here. When you find the Laplace transform, so 1 upon a square plus 1 will be there, because a upon a square plus a square, and for this you will have a 1. Okay, you have here 2 e to the power minus pi s plus 2 e to the power minus 2 pi s. Similarly, e2 e to the power minus 3 pi s goes on, right? When you do this, so you have this, so you can see easily what is the common term here. So 1 upon s square plus 1plus 2 e raised to the power minus pi s. to the power minus pi s. Sorry, this is minus na? Yeah, this will be minus na. Maybe 1 minus r is the e to the power minus pi s. So finally you have 1 upon s square plus 1 and 1 plus e to the power minus pi s, okay, upon 1 minus e to the power minus. Signal you can easily do. Let us discuss some typical waveform you will encounter. Awkward type. Can anyone try to write the mathematical expression of ut? At least we should look first you do the simple synthesis starting from 1, right? Starting from 1, that means there is a ut. By ut there will be an ut, so that you will start the 1, but it is decreasing here, decreasing, we are subtracting, that means first ut, then we subtract with a negative slope, then at this point we launch a positive slope, that means first ut red color, then this blue color, then we need to make 0 at 2, so this cancel, that means your x of t is the 1 ut, that is ut, then what is the slope? Slope is the minus 1 by 2, that is minus 1 by 2, sorry, slope is acting at t equal to 0 na, so slope is the minus correct, minus 1 by 2 to r t or t ut, okay. Then here you are having the positive slope of the same value to cancel positive and negative slope, okay. Okay, then write that plus r of slope same half r of t minus 2. This is the equations. This is the equation. Okay, that is first is the ut. Okay, see here ut. Then, but it is not going this straight, but it is reducing. If reducing, then if I subtract, if I subtract this value, for example, let's say this is at, let's say for 1, for half, sorry, it is 1, yeah. For 1 it is half, for 1 it is half, okay, this value half of, this is 1, at this value it is minus half, because this function has the value of so you need to write the equation itself. Yeah, I have shown it correctly, but it should be like this, na? You see. Now you understood. This is the slope is half. I mean minus half. Okay. You see here this slope. For example, at 1 it is minus half, and 1 minus half is the half, that means this value is half. Similarly it goes on. So you have x of t equal to ut half rt and plus half rt minus 2. So Laplace transform will be the 1 upon s minus half s square, okay, half s square plus half s square e to the power minus 2s. This is the Laplace. What about this form of the signal? Let's say this is 3, this is 0, this is 2. How to do this? This is easy. What is the slope? 2 by 3, sorry, 3 by 2, and launch at equal to 0. So r of, what is the slope? Slope is the 3 by 2 rt, and keep on launching is going on, but you need to same slope but negative sign you will be launching here. So the what is that value? Minus 3 by 2 minus 3 by 2 r of t minus 2. Clear? We are launching, so the function will be like this. But we need the 0 here. At this value we need 0. Okay, how to get? Because this becomes like this. If I launch another negative step here, I will have a 0. Negative step of the value 3. Negative slope at the value 3. Okay, the value of 3. That means minus 3 u of t minus 2. U of t minus 2. This is the total function. This is the x. Once again, this slope 3 by 2 rt. I put a negative slope at same slope but negative at 2. So I think so the signal now becomes this. But I want to cancel all this. That means to cancel, this is a positive 3. I need a negative 3 at t equal to 2. Okay. So you can easily find out the x of s 3 by 2 s square minus 3 by 2 s square e to the power minus 2s minus 3 upon s e to the power minus 2s. Here, okay. Then we will apply one formula for a periodic functions. I had told you in the last class we have a formula for the periodic signal. We had discussed this function, right, starting from t equal to 0, pi, this is the 1, 2 pi, like this. I have told you if this is your xt, xs can be found by what is the relation? E 1 minus e to the power minus ts into Laplace transform of one period. What is the t here? This is periodic, so t is your pi. What is the one period here? This one. So one period can be written as one period. x1t can be written as sine of t. We have already discussed, plus sine of t minus pi. Sine of t plus sine of t minus pi. What is the Laplace transform of one period? 1 upon s square plus 1 minus e to the power minus pi s. equal to pi, put these values. So x of s will be the 1 upon 1 minus e to the power minus pi s t equal to pi into 1 upon x square plus 1 1 minus e to the power minus pi s. So finally we got 1 upon a square plus 1 1 minus e to the power minus pi s upon 1 minus e to the power minus pi s. 1 plus na, otherwise it will be cancelled out 1 plus. So we got the answer. Same result we found before also. See, by direct analysis, right? Yeah. We'll now find the inverse Laplace transform using the Heaviside expansion. You have already studied all this expansion type in your intermediate. That is your not expansion exactly, that is the partial fraction, na? Yeah. Or we can also call it is called as the Heaviside expansions, partial fraction or Heaviside, the famous engineer. You can suppose you have a non-repeated linear terms in denominator. For non-repeated linear term in denominator, for example x of s, you need to expand it, 2s plus 3 upon s square plus 3s plus 2. So I can write repeated term here, s plus 1 into s plus 2. So you can write, this is case for the non-repeated linear terms in the denominator, a of s plus 1 plus b of s plus 2. How to find the a and b? A is either you have done it done in the intermediate as a coefficient, equating the coefficients of the numerator. Here same thing is done, but in a little different way. So a you can find like this, a is equal to multiply s plus 1 both the side. So when I multiply s plus 1 this here, so you have like this, that is 2s plus 3 upon s plus 2 and a plus s plus 1 upon s plus 2 into b. If I take s equal to minus 1, this will be 0, okay, and this side will be the, take s equal to minus 1, so this side will be the minus 2 into minus 2 plus 3 minus 1 plus 2, which is equal to minus 2 plus 3 is 1 1 upon 1, which is a, which implies a equal to 1, right? In a similar fashion multiply this. So how you write in a organized manner? A is equal to s plus 1 into xs evaluated at x equal to minus. Similarly b can you write s plus 2 into x of s evaluated at s equal to minus 2. So you have 2s plus 3 upon s plus 1 evaluated at s equal to minus 2, which is minus 4 plus 3 upon minus 2 plus 1 minus 1 upon minus 1, which is again 1. So now you can write x of s is equal to a 1 upon s plus 1 plus b 1 upon s plus 2. Now you know that you look up your Laplace transform pair table. You will get that x of t, what is the Laplace transform for which function has the Laplace transform of this? That is e to the power minus t ut plus e to the power minus 2t. Very easy. So this way we found the inverse Laplace transform. This we have synthesized non-repeated linear terms. Okay. Now we'll move to the next, that is your repeated linear terms. Repeated linear terms. Okay. For example, you have x of s is equal to s plus 2 upon s plus 1 square into s plus. You have repeated terms. How to extend it? That is, see here. Whenever you have a repeated terms and multiplied with another terms, you will be expressed like this: s plus 1 simple term, then b upon s plus 1 square. Suppose it has been a s plus 1 q, then s plus a upon s plus 1 plus b upon s plus 1 square plus c upon s plus 1 q. Then you write next term, then c upon, right? So this and this can be found directly. See here, as per the I have told you, that is b is equal to s plus 1 square into x of s evaluated at s equal to minus 1. That is s plus 2 upon s plus 3 s equal to minus 1. That is minus 1 is 1 upon 2. Okay. And you can easily found the c also. C is equal to, what is the term c? S plus 3. So s plus 3 into x of s evaluated at s equal to minus 3. That is s plus 2 upon s plus 1 square evaluated at s equal to minus 3, which is minus 1 upon minus 3 plus 1, that is your minus 2. Square of minus 2 is the 4. So minus 1 by 4. But you cannot find this way. This way, what I do normally, I don't, Heaviside says that you differentiate it. Okay, you differentiate this side and this side, then put the value for the this a. But instead, because already, as you have already found the two unknown, that is b and c, it is only one step away to find the a, just comparing the coefficient of any side. So here I will compare the coefficient of s in both the side. So before that, you should see that where a also involves. Okay. So you can write x of s like this. I can write x of s is equal to s plus 2 s plus 2 upon s plus 1 square into s plus 3, which is equal to s plus 1 square into s plus 3 upon, here is a s plus 1, so you have a into s plus 1 into s plus 3 plus b into s plus 3 plus c into s plus 1 square. So it is easy to find the a if you compare the square term. In the square term, you have, see, coefficient of s square, coefficient of s square, okay, that is a equal to minus c, which is 1 upon 4. So finally you have x of s is equal to x of s is equal to a, what is the a we got, a we got 1 upon 4, 1 upon 4 upon s plus 1, and what we got, the b we got, half. Okay, now a got 1 upon 4. Okay, and we got the b is the half. B, okay. Okay, we got the b equal to half into s plus 1 square, and c is equal to minus 1 upon 4. This one, hope it is you don't have any doubt. Then look up for the Laplace transform pair. So you will get 1 upon 4 e to the power minus t plus half t e to the power minus t. Is clearly seen, minus 1 upon 4 e to the power minus 3t u t. Clear? Then next is the denominator contains pure quadratic terms. Denominator contains pure quadratic terms. For example, part C is the x of s is equal to s upon s plus 1 into s square plus 2s plus 5. You can see you cannot factorize without complex variable or complex or imaginary roots. So for this you can write a upon s plus 1, simple term a. For quadratic term you write bs plus c. Bas, bs plus c. So for a you can easily find out the things I have already discussed. A is equal to s plus 1 x of s evaluated at x equal to minus 1, that is s upon s square plus 2s plus 5 s equal to minus 1. So minus 1 upon 1 minus 2 plus 5, so minus 1 upon 4, minus 1 upon 4. Okay, you have minus 1 upon 4. Now you do a either way you can do, you differentiate both the side, then find the coefficient or equate with the coefficient, or you can directly equate with the coefficient. See how I am doing here. So s upon s plus 1 into x square plus 2s plus 5 is equal to s plus 1 into s square plus 2s plus 5 equal to a into s square 2s plus 5 plus bs plus c into s plus 1. Now find the coefficient of the s square. What are the coefficient of the square? A. Coefficient of the square is the a plus b, and this side no s square, 0. So you get the b is equal to minus a. B equal to minus a. If b is equal to minus a, so what is the b? So b equal to 1 upon 4. Okay. Then how to find the c? Same way, any coefficient you can do, or you can say I will do with the c. You have to always strive to get the easiest way. If I compare with the coefficient of s, then already it is existing. So coefficient for a, then for the s you have c, for the s you have b. Instead you just look for the easiest path. I go for the zero coefficient of the constant term. Here there is constant term is 0. That means 5a, see, a into 5, then c coefficient, na, because b is the b has the a square s, but c has the constant term which is 0. So c equal to minus 5a, that is 5 upon 4. How easily we are getting it. So ultimately we got x of s is the a. A is the minus 1 upon 4, minus 1 upon 4 upon plus upon s plus 1 plus 5 by 4, 1 by 4 into 5 by 4, you can take out the 1 by 4 common, s plus 5 upon s square plus 2s plus 5. So now question is how to find the Laplace transform of this. This is very straightforward, but this is not the straightforward. Okay, so let us write, you know this, but you don't know this. So I will proceed line by line. So minus 1 upon 4 upon s plus 1, because we know this, we will just carry 1 upon 4 s plus 5. How to factorize it in the form of sine and cos? So a square plus 2 into 1 into s plus 1 square minus 1 square plus 5, then that is minus 1 upon 4 s plus 1 plus 1 upon 4 s plus 5. I can write this as the s plus 1 whole square, that is 2 square. So just carry on like this, minus 1 upon 4 upon s plus 1 plus 1 upon 4